He's a local in the sense that he's a professor here at Carnegie Mellon. So Avram, for a very long time, has been one of the real dual leaders simultaneously in learning theory and theoretical computer science. Very cool combination, and both of those skill sets have found good application now in game theory. So looking forward to hearing about that now.
Thanks, Tim. All right. So I'm going to talk about some very simple online learning algorithms that have some really nice properties, nice guarantees you can get using them, and connections they have in game theory. So when you're in a multi-agent setting and you want to talk about players adapting their behavior and what kind of overall behavior you can expect. Okay, so I'm going to sort of structure this as a kind of a guide. So I'm your tour guide here. And so the itinerary on our tour is as follows. So the first stop on our tour is I'm going to talk about algorithms for a very nice problem of minimizing regret and combining advice. Eva Tardish talked about this a bit in her talk on Monday. And she mentioned that there were some very simple and nice learning algorithms that allowed you to do this, and that I would talk about them, and indeed I will. So I'm going to first talk about that. So in particular, this randomized weighted majority or multiplicative weights algorithm, and it has some really nice guarantees you can get, and connections of this to minimax optimality in zero-sum games, and also something known as coarse correlated equilibria. Then I'll talk about an extension of this to trying to do online learning from very limited feedback. This is classically called the bandit problem. And we'll look at algorithms for that and how we might use that for some online pricing or auction problems. Then I'm going to go back and look at a stronger kind of regret guarantee known as internal regret and connections it has to something called correlated equilibria. So we'll look at algorithms for that and show if everyone is optimizing their behavior in this way, that the play overall approaches correlated equilibria, or the set of correlated equilibria. And then the last stop, I'm going to take a step back and say, well, all right, so far we've been talking about, in the first three, can we talk about individual behaviors where we can use them and overall play will approach some equilibrium. But if we're, say, the overseer of some game that, some multi-agent setting where there are both good equilibria and bad equilibria, and maybe the world is somehow stuck in a bad equilibrium, and what can we say about strategies for an overseer for helping to kind of nudge behavior over into, from bad equilibria to good ones? And so we'll look at a model for that. Okay, so that's the plan. The first two will be roughly first two today and the next two tomorrow. Okay. First. Okay, so just as motivation, so consider the following setting. So let's imagine that every morning you need to pick one of n possible routes to drive to work. So there you are, trying to find some way to drive to work. And so, but traffic is different every day, so it's not clear a priori which of these is the best to take. So let's say that, you pick a route, and when you get there, you find out, how long it took you, 32 minutes. And maybe, you talk to your friends and you find out how long other routes would have taken, or you look up online how long it would have taken you had you gone some other way, or maybe not. And then the next day you do the same thing. Traffic is different. You try something else. So maybe the next day you pick a different route and it takes you 29 minutes. Is that because you were smarter in your route, or because traffic wasn't as bad that day, or whatever? Who knows? The question is there a strategy we can use, every day picking a route, so that in the long run, at the end of the year, whatever the traffic actually was that year, you've ended up doing nearly as well as the best fixed route you could have taken in hindsight. So nobody, none of your friends can say, oh, I always go this way, and that's much better. You'll have done nearly as well as any fixed route you could have taken. Okay? And the answer is yes, you can do that. If the answer was no, then this would be less interesting. So, and by some very nice algorithms. Okay. So let me just more generally talk about this framework of sort of no regret or no diminishing regret algorithms for repeated decisions. So a bit more generally, the setting is we think of an algorithm that has n options. Think of them as sort of rows in a matrix. And every day, the world chooses some cost vector. So there's some n rows. There's some. Think of every column as a cost vector. So what's the traffic pattern like? So think of a column here as a traffic pattern. How long would it take you had you chosen this particular way to get to work? Okay, and maybe there's an infinite number of different traffic patterns, or maybe only a finite number. Okay. And the way the game works is every time step you pick a row, so you pick a way to get to work. Life picks a column. Life picks what traffic is going to be that day. And you pay this little entry in that square. That's the cost of using this route on that kind of traffic. Does that make sense? Right? So you pay the cost for the action you chose. You get, in the basic model, we'll look at the full column as feedback, so you get to find out how long it would have taken you had you done something else that day. Okay, or in the bandit model, you just find out just that entry there. If you want to find, you can't actually find out because the day is over. Had you done that, you didn't do that. For this to make sense, to talk about the kind of things we want, we'll need to assume some bound on the maximum cost. So it can't be the case that you pick some route and fall off a cliff and die and get a cost of infinity, because then game's over. So there's no way you'll end up doing nearly as well as the best in hindsight if there's an infinity sitting in there. So in particular, we'll assume all the costs are between 0 and 1. Let's just call it hours. Okay, so no matter what you do, it's never going to take more than an hour to get to work. Okay, so good. So given that setting, the average regret in t time steps is just the following natural thing. Okay, you've run your algorithm for a year. You look at, on average, how long did it take you per day to get to work? Say that was 32 minutes. You look at, on average, what was the best fixed choice in hindsight? Maybe the best fixed choice in hindsight, the best fixed route, on average, took 29 minutes to get to work. That difference, that 3-minute difference, is your regret. Your regret, 3 minutes per day, not having done that, and having done your algorithm, rather than, in hindsight, gosh, I should have taken this route every day. That would have been better, that gap of 3 minutes. That's your regret. Does that make sense? So how much you regret not doing that instead of that. And what you want is that to go to 0 or better as t gets large. Okay, if you have an algorithm that can do that, it's called a no-regret algorithm. Okay? It could go better because we're just comparing the best fixed row. So it's possible your algorithm actually did better than any fixed strategy. But okay, good. So that's what we want to get. We want to say that our algorithm over time, on average per day, will end up doing nearly as well or better than any fixed choice in hindsight. Okay? So let's just get a little feel of this sort of thing, some intuition. So let's look at a very simple example. Say there's only 2 ways to get from our start to our destination. And let's say there's only 2 kind of traffic patterns in the world. Say there's this kind of traffic pattern where the top route's congested and the bottom route is free. So let's say the top costs 1, bottom costs 0. And there's this kind of day with the other way around. The top route is free and the bottom one's congested. So the top costs 0 and bottom costs 1. Okay? So there's 2 kinds of days in the world, and there's 2 choices our algorithm can make. Okay? So one first point to make, we're not trying to compete with the best adaptive strategy in hindsight. So in hindsight, we should have done maybe this on day 1, and that on day 2, and then top on day 3, and bottom on day 4, and bottom on day 5, and top on day 6. No way, then we have a total cost of 0, right? In hindsight, there was always one thing to do that day. There's no way we can compete with that. Right? Just trying to compete with the best fixed choice in hindsight. Okay? And the other thing is that, so we can potentially do much better than minimax optimal. So what do I mean by best fixed path? So if in the end, at the end of the year, this bottom was congested 70% of the time, so 70% of the days were this kind, and 30% of the days were that kind. All right? The best fixed choice in hindsight was top. That would have only been congested 30% of the time. So we would like our algorithm to have only gone a congested route 1% of the time. Okay? And notice that could be much better than minimax optimal. Minimax optimal in this game is 50-50, right? This is, so if you think of the worlds being out to get, you're going to flip a fair coin. But maybe it just turns out that the top is always good and bottom is always bad. You would feel really stupid playing 50-50 the whole year if you could have just gone the top the whole time and never paid anything. Okay? So in that case, you should really get a cost that's very close to 0. Now, it could be much better than the minimax optimal.
Does that make sense? Yeah.
Do you have a bit of intuition for why you never do much worse than minimax optimal?
Oh, well, because in hindsight, good. So the minimax optimal strategy is some probability distribution over rows. And so in hindsight, the performance of the minimax optimal is the weighted average of the rows that it uses. So if it's P1, P2, it's P1 times how well this does plus P2 times how well that does. So the best fixed row in hindsight is always at least as good as minimax optimal. Because minimax optimal is a weighted average. And so since you're doing nearly as well as the best fixed row, good question.
Sorry. How do you model the world life fate action? Is it adversarial or?
Okay, good. So that's good. That's my next slide. Right. So we're going to view the world life fate as an unknown sequence. So not necessarily stochastic. It's some arbitrary sequence. Okay, so we're not going to claim to know anything about traffic. It's a, there's going to be some sequence in the future, but it's not going to depend on our algorithm. Okay, so the world in advance commits to, for the next year, what traffic is going to be like, on day 52. It's some crazy sequence depending on construction and whatever, but all those issues don't depend on our choices. So nobody looks at our choice and then decides to change when they're going to do construction or whatever it is. So it's adversarial but fixed in advance. And our goal is to do well no matter what the sequence is. So formally what I want to say is for any fixed sequence, fix the sequence, now run the algorithm. What we want to do is do well in expectation over our internal randomness, whatever that sequence is.
Just to be clear, that internal randomness that generates one sequence, are we imposing that it's more chosen independently each period? Or?
So let me get back up. The sequence is picked by the world, by fate or whatever. That's not necessarily picked at random. That's some arbitrary sequence. So you can think of it as the following kind of game. Someone else picks a sequence of, the world picks what traffic is going to be like the entire year. Now your algorithm can flip coins in deciding what it's going to do. What you want is no matter what that sequence is, over the randomness in your algorithm and choosing what to do, you end up doing nearly as well as the best fixed choice for that sequence. So fixing the sequence, there's now a well-defined best thing to do. Now we can imagine watching the algorithm behave and asking, did it approach that or not? But the sequence doesn't look at the algorithm and say, oh, I'm going to change the future based on what the algorithm says.
Just the question of the size of the agents when they pick the algorithm, do they assume anything about how this technology is created?
Is there a prior? No, there's no prior. So in fact, actually, you can actually have a sequence. So in fact, the sequence can depend on the algorithm. So in fact,
What is meant by doing well in expectation? What do you expect?
So the algorithm itself is going to say, today, with probability 0.7, I'm going to take the up route, probably 0.3, I'm going to take the down route. So I'm going to view my payoff as 0.7 times that. In the same way, like for a mixed strategy. When you have a mixed strategy in the game, you view the payoff as the expected value. So that's what I mean. That's what I mean. My expected payoff or expected cost should be, yeah. So I want to view the dot product. My algorithm might say a 0.7 probability, I'll pick this, 0.3 probability, I'll pick that. If the world chooses the first column, I want to view my payoff as the dot product of my probability vector and this column here. Or my cost is that. So I want to, does that make sense? So if my algorithm might say with a 0.7 chance I'm going to take the up route, 0.3 chance I take the bottom route. If it turns out the up route's congested and the bottom route's not, my cost is 0.7 because there was a 0.7 chance I took that. That's what I mean by my expectation. And actually, in fact, this sequence can actually depend on the algorithm. It's just not allowed to depend that day. And what I mean is the world picks what traffic's going to be like today, and then I pick my route today. The world doesn't see, I'm going to go this, and then changes traffic today based on what I'm about to do. Okay, so in fact, it's allowed to define future construction, based on what I do today. But then I still want to compare my performance to the best I could have done on the actual sequence I saw.
So you said that maybe we could do much better than the best fixed strategy with some adaptive thing. So, but do we know? Are we setting the bar too low, or like is there maybe some theorem that there can always be a time when we don't do any better? Or maybe we could always do better.
Oh, I see. So we will look at stronger guarantees. However, if the world was IID, imagine the world was, there's a fixed distribution over traffic patterns, and each day is independently picked, then the best choice is a fixed strategy. So in that case, there's no way to do better. So if the world is a fixed distribution, the best you could do is, every strategy has a well-defined expected cost under that distribution. So, yeah. And there's no way you could do better, because for any algorithm, you go and then the world picks, and what can you do? Good. Okay, great. Yeah, and so in fact, for this goal, right, your algorithms will have to be randomized. And the same reason that, if you're playing rock, paper, scissors, you have to be randomized, otherwise you lose every time. Okay. So let me just give a sort of a very abridged history of these. So it goes back over 50 years. So Hanan and Blackwell gave algorithms that have regret square root of n over t, where n is the number of action choices, the number of rows, t is the number of time steps. Rephrasing, if you ask, how long do we have to play to get our regret down to some epsilon equals 3 minutes? Okay, like, 3, I guess if we're scaling to hours, down to a regret of 0.020, whatever, 4 hours. Okay, then it's this many time steps, n over epsilon squared. If I want to get my regret down to epsilon, I need to play n over epsilon squared times. And this actually has the optimal dependence on t. This 1 over root t is optimal, the optimal regret with as a function of t, or in terms of epsilon, if I want to get my regret down to epsilon, this 1 over epsilon squared is optimal as epsilon. And so game theorists kind of viewed number of choices as a constant. There's a constant number of choices, and t is the important quantity, so kind of pretty much done. Now, actually, before going on to the subsequent, let me just say quickly, why is this optimal in t? Here's a very simple way to see that. Let's go back to our very simple game with 2 choices and this 2 possible routes and 2 possible worlds. Imagine that the world actually just every day flips a fair coin to decide whether the top route will be congested or the bottom route will be congested. Whatever your algorithm does, 50-50 chance you took the congested route, right? I mean, if the world 50-50 chance is this kind of world or that kind of world, whatever your algorithm does each day, 50-50 chance you take the congested route. So no matter what algorithm you pick in t days, your expected cost is t over 2, right? Because world's 50-50. However, in hindsight, the number of times the top route was congested might not be exactly t over 2. The number of times the bottom route's congested might not be exactly t over 2. In fact, it's a question, if I flip a coin t times, how many heads, how many tails, the better of the 2 routes is the expected value of the minimum of heads and tails if I flip a coin t times. And the expected value of the minimum is not t over 2. It's t over 2 minus roughly square root of t. If I flip a coin t times, I'm not going to always get half heads and half tails. On average, one of them is going to be about square root of t bigger, and one of them will be about square root of t smaller. Expected value of the minimum is t over 2 minus root t. Divide the whole thing by t. My per day gap is 1 over root t. So this example shows you can't beat 1 over root t regret, because even in the simple case, you can't do it. So this kind of bound as a function of t is optimal. So game over. Okay. But this came back in the world of learning theory, where we kind of think of n as a whole bunch of different prediction strategies we might be using for some prediction problem. And in that setting, it's very natural to think of n as extremely large. And then this is kind of a bad quantity here. And we have like a whole bunch of prediction rules. We're trying to perform nearly as well as the best prediction rule in hindsight. And this really nice result of Littlestone and Wormuth with a weighted majority algorithm and then extended in various pieces of work gave you a bound on cost where your cost over time will be most epsilon times the best choice in hindsight plus a log n over epsilon. When you solve for epsilon, you get regret of square root log n over t. Okay? So the n got down to a log n. And so the number of time steps it takes us to get regret down to epsilon is order a log n over epsilon squared as opposed to n over epsilon squared. And that can be much better if the number of choices is extremely large. Okay. And this log n is actually also optimal now as a function of n. Okay. And then there's been a lot of work on the exact constants, second order terms, and many other issues involved. Okay. And then extensions to the bandit model where you get limited feedback, and that adds an extra factor of n. Okay, so that's a very abridged history, and what I want to do is talk about this algorithm here. All right? Okay, so to think about this, let's look at the following problem. So I'm going to slightly change the scenario a bit, but then we'll go back to this one, the problem of combining expert advice. Okay, so how does this work? So let's say we would like to predict the stock market. So what we do is we ask n experts for their advice. You know, will the market go up or down today? Okay, and then we want to use their advice to somehow make a prediction. Okay, so for example, let's say, you know, we ask a few experts. We check to see if our neighbor's dog is wagging its tail today. And then based on those, we can, you know, we get predictions of whether the market's going to go up or down. And then we use that to somehow make a decision. Then we find out what actually happened. A number of you have noticed the neighbor's dog is doing quite well. Okay, so what we like in this world is, the question is there a strategy that allows us to do nearly as well as the best of these in hindsight? So had we, you know, at the end of the year known, you know, which one of these did, you know, maybe in hindsight at the end of the year one of them was actually pretty good, well then we would like to do pretty well. If they're all bad, then we'll be bad. Okay, but if one of them was good, we would like to do well too. All right? That's what we want. Had we known in advance which one was best, we could have just followed that one, but we don't know in advance which one is best. So we're kind of asking, you know, what is the penalty for not knowing in advance which one of these is best? Can we have an algorithm that initially has no idea, but even for an arbitrary sequence of events, an arbitrary sequence of stock market ups and downs, in the end does nearly as well as if it had known in advance which one of them was going to be best? Right? That's a nice thing to be able to do. I like stock market because this word expert really is in quotes. Normally you think of an expert as someone who knows something. Here I just mean an expert as someone who's willing to give you their advice, not that actually knows anything. So that's why financial makes a lot of sense. So an expert is someone with an opinion, not someone who necessarily knows anything. So they could be all bad or someone good or whatever. If any of you are in finance, I'm sorry. Okay. So let's start this with a simpler question. So here's something we can just do much easier. Suppose we again have n experts, and one of them is perfect. It never makes a mistake. Okay, so every day they're going to predict market goes up or down, and I don't know which one in advance, but one of them is perfect. It's going to get all correct. Okay, we just don't know which one. Can you find a strategy that combines their advice? So does the setting make sense? Every day, the experts all give you their end predictions. You look at them. You have to make your own guess, market up or down. Then you find out what actually happened, and you want to be correct. Okay? And let's say you make a mistake. If you said one thing and the market did something else. So in this case, if one of them is perfect, can you find a strategy that makes no more than log base 2 of n mistakes? Can anyone see like a really simple strategy we could use?
Anyone want to volunteer a simple strategy? Okay.
Never, each day, just rip out of your address book the person who ever made a mistake.
Okay.
So each time, well, I guess if it's about even, say up and down, then keep trying.
So you throw away the people who've made a mistake in the past, and then what do you do with the rest? So say day 1, take the majority vote of the rest. Good. So just go with the majority vote of what they say, and then when you see what actually happened, throw away the ones that made a mistake. Right? Every time the majority is wrong, you get to throw away at least half of what's left. So every time you make a mistake, sometimes you don't make a mistake, you get to throw away some experts. But for sure, every time you make a mistake, the number of experts left goes down by a factor of 2, at least, because the only way the majority is wrong is if more than half give the wrong answer. So every time you make a mistake, the number of experts in the system drops by at least a factor of 2. You can only cut by a factor of 2, log base 2 of n times, till you're down to the 1 left. Right? Good. Okay. Right, so that's just what we said. One thing that's nice is log n, right? So that means you can have n being very large and you don't make too many mistakes. So that's great. That's log. Right, log is good. Okay, so, all right, so it's called the halving algorithm. But what if no expert is perfect? Okay, so now, what if no expert? So one thing we could do is just run the above procedure, okay, until finally we've crossed everyone off. At that point, we've made log n mistakes, and every expert has made at least one mistake. So just bring them all back in and run it again. That'll make log n, at most, log n mistakes for every mistake of the best expert. Okay, so it makes the most log n mistakes for every mistake of the best expert, plus an initial log n mistake at the very beginning. So that's log n times as many mistakes as the best expert. Can we beat that? All right, so just as an initial algorithm, we can easily get log n times the best expert by just putting them all in the system, running that, cutting them until they've all made, we've thrown everyone out, and just restart. Everyone see that? So, but it's kind of wasteful. So every time we just sort of hit ourselves in the head, restart, forget everything we've learned. Can we do better? Right? And the answer is yes, in fact, by a very natural kind of thing, which is since we're not assuming any expert is perfect, when someone makes a mistake, you shouldn't throw them out. Just lower their weight. Just pay less attention to them. In particular, we're going to do that multiplicatively. So this is the weighted majority algorithm. You start with all experts having weight 1. You predict based on a weighted majority vote, which initially is just a majority vote. And then you penalize mistakes by cutting their weight in half. Okay. Why half? Why not? Well, why not half? Okay. We'll go back to that. Okay, so, does the algorithm make sense? So they tell you what the market's going to do. You make your prediction. You find out what actually happened. For all the ones that made a mistake, you penalize them. You knock their weight down by a factor of 2. And so now you have different weights. You get their votes, take away the majority vote. Okay, so this is sort of a little, they all weights 1, they made predictions, so this is like yeses and nos. Okay, to have ups and downs. But the algorithm makes sense? So, right, so just cut their weight in factor of 2. Okay. Okay, now claim that this guarantees, so by using this, we'll end up with doing, we'll be able to improve. We had log n times as many mistakes as the best expert. We're going to be able to reduce that down to about 2.4 times number of mistakes of the best expert, and then we'll improve even more. Okay, so let's analyze this algorithm. Okay, the algorithm was, well, we remember the algorithm. Okay, we want to claim we do nearly as well as the best expert in hindsight. To analyze this, we're going to look at 3 quantities. Okay, so the analysis is going to fit here, and we're going to look at 3 quantities. The first is the number of mistakes our algorithm has made so far. I'll call that capital M. The second is the number of mistakes the best expert has made so far. I'll call that little m. And the third thing is capital W, which is the total weight of all the experts. Okay, we're going to look at those 3 things. Okay, so the first thing to notice is that every time we make, first of all, the total weight in the system never goes up because the algorithm never raises anybody's weight. It only penalizes them for making mistakes, right? So it's the total weight in the system never goes up, and every time you make a mistake, the weight drops by at least 25%. Can you see why that's true? The weight drops by at least, because you have, there's some amount of weight in the system here. Just think of this as the total weight in the system. And then you went with a majority vote. So some weight said something, this weight said up, this weight said down, and so you went with the majority vote. And if you were wrong, it means more than half of the weight did the wrong thing, and you took these guys and you cut their weight in half. So if you cut more than half of the weight in half, you got rid of, the total weight in the system dropped by at least half of this region, so at least 25%. Right? So we took more than half of the weight and cut it by a factor of 2. So the total weight in the system is guaranteed to drop by at least 25% every mistake, and it might even drop by more, and it might even drop when we don't make a mistake. Great. So one thing that says is after m mistakes, the total weight in the system is at most the initial, remember initially everyone had weight 1, and there's n experts, n times 3/4 to the m. Right? Okay. Now the weight of the best expert is exactly 1/2 to the little m, because he made little m mistakes, and the algorithm says when you make a mistake, penalize by cutting by factor of 2. So its weight is exactly 1/2 little m. The last step in the proof is just to notice the total weight in the system is greater than or equal to the weight of any individual one, since this is a sum, and the weights never become negative. So the sum of all the weights is at least as big as the biggest weight. So let's just solve. This quantity is greater or equal to this quantity. So let's see, let's move this 1/2 the little m over to a 2 little m here, 3/4 the big M to a 4/3 the big M over there. Take log base 2 of both sides. Log base 2 of this becomes little m plus log n. Log base 2 of this, m times that, move over here, becomes 2.4, 2.4 something, something, something. And so what this says is our number of mistakes is at most 2.4 times number of mistakes of the best expert, plus this additive log n. You can't get rid of the additive log n because, why? It's the sort of classic kind of, this classic scam where you set up, n newsletters where each one predicts the market, randomly. And after log n days, one of them just got it right every day. So you can't kind of, like if they were all random, after log n days, you'd sort of expect one of them was right the whole time, and your poor algorithm, what's it going to do? So that's sort of why you have to lose the log n. Okay, so 2.4, so that's pretty good. It's a constant ratio. If the best expert made a mistake 1% of the time, you're making a mistake about 2.4% of the time. It's not great, though. If the best expert made a mistake 20% of the time, you're making a mistake 48% of the time. That's not so good. Okay? But it's better than, we got it down to a constant. So let's try to make this even better. Everyone okay so far? So let's try to make that even better. So we're going to make it better using randomized weighted majority algorithm with two things. First of all, this is just saying what I said, 2.4 times that is not so good if the best expert make a mistake 20% of the time. Okay, so first of all, instead of doing a majority vote, we're going to treat these as probability. So if, this is 60% said one thing and 40% said something else, rather than going with the majority, we'll flip a coin with probably 0.6 do this, probably 0.4 do that. Okay? Let me match the slide. 70? 30. There. Okay. Okay. So why do this? Well, because, it's a game against a world. So randomization, we should use randomization. Where in the analysis is this helping? It's because see, in the previous analysis, there was this worst case. The worst case was 51% of, right, what was the worst case? The worst case was 50% of the weight did the wrong thing. Right? The worst case was 51% did the wrong thing. We went with that and did the wrong thing. With this approach, if 50% does the wrong thing, the reason why this was the worst case is we only got to penalize the weight by cutting these guys in half. So we only got to remove 25% of the weight, or 25.5% of the weight of the system, right? Because the amount of progress we make is how much we get to lower the weight. So if only 51% gets the wrong answer, we only get to lower we only cut these guys. But with this algorithm here, if this happens, sure, we only get to cut these guys, but at least we have a 49% chance of getting the right answer. If an adversary wants to cause us to have a very high probability of getting the wrong answer, it better make a large percentage of the weight say the wrong thing, but then we make more progress because we get to cut more weight from the system. So this way we get to tie the probability we make a mistake with the amount of progress we make. And that's what we want. So the probability we make a mistake is the probability mass that's on the wrong answer, and that's nicely tied to how much weight gets removed from the system. That's why this is helpful. It makes it so there's no longer a worst case. Yeah?
Whenever somebody is sort of giving a wrong answer, you're actually cutting the weight by half. You're cutting the weight by half whenever somebody is actually giving a wrong answer prediction. So shouldn't it be like, if somebody actually gives the right answer, this weight should go and add up to somebody who's given a right answer symmetrically, so that you make up a bigger component of getting the truth or right prediction.
If you want, so I like to think in terms of the weights directly. If you want to think of renormalizing the probabilities, suppose I now multiply everybody's weight by 1.2, it doesn't change anything because so it's just the relative value. So by not being penalized, you're being rewarded. If I were to rescale the weights to always sum to sum to 1, then you'd be rewarding the ones that got the right answer. From the analysis, it's just easier to think about only penalizing when you make a mistake. The second thing we're going to do is, rather than penalize by multiplying by a half, we'll hit them with less big of a hammer. We'll just multiply them by, say, 0.9, by 1 minus epsilon, less penalty. If we do that, you get this sort of bound on the expected. This is a messy quantity, but the expected number of mistakes is at most this quantity here. Taylor expansions, this is about 1 plus epsilon over 2 times little m plus 1 over epsilon log n. If you just want to plug in some numbers to get a feel of this, okay, if I use epsilon as a half, I get this quantity, 1.39 times number of mistakes of the best expert plus 2 times natural log n. If I plug in epsilon as 1/8, I get 1.07 times number of mistakes of the best expert plus 8 log n. Notice this is starting to get quite good, right? Even if the best expert makes a mistake 20% of the time, this is 1.07 times 20% plus an additive term. This is growing. As I bring epsilon down, this part gets worse, this part gets better. Because as epsilon goes to 0, it means I'm learning more slowly, so it just takes me a little bit longer. Okay? But I end up getting nearly as well as the best expert. Yeah?
I'm wondering if we can do this well in polynomial time.
So the algorithm is polynomial in what? So polynomial in the number of experts? Say?
No, the number of steps.
Okay, yeah. So the algorithm is polynomial in both. I mean, the algorithm is very simple. It's just...
You seem to be doing arithmetic on numbers the size of 1 over 2 to the n.
Oh, you're worried about like the bit precision and so forth. Yeah. So you can... nothing depends on sort of high precision. You only need precision... like log 1 over log n over epsilon bits of... You really don't need very much precision.
Fix the precision and below that.
Yeah, that's right. And then that'll just come in as a little lower order term here. So you can... I guess, let's see. So you probably want log t... If you want to talk about as a function of t, you'll need the precision to grow, but logarithmically with t. But you're not going to need much precision. In fact, you can just keep the log. In fact, you only need to really keep around the number of mistakes each expert has made, because you can calculate the weights from that. And so, yeah. Right, when you actually go to implement it, you don't want to implement it the way I'm talking about it, because the numbers will get very close to 0. So you want to keep around just the logs. Okay, so how do we analyze this? So the analysis will just be a bit of a generalization we just did. So I'm going to give this proof. This is, yeah. So the proof is going to fit here. So how do we analyze this? So let's say at time t, we have a fraction ft of our weight on the experts that made a mistake at that step. Okay? So let's say that we had... let's see, which ones we want to say made a mistake? Let's say these guys. So we had ft, 1 minus ft. Let's say at time t, we had an ft fraction of our weight on the experts that made a mistake at time t. Right? So that means we have probability ft of making a mistake. because our algorithm, flips a coin with probability ft picks this, with probably 1 minus ft picks that. So if ft, fraction of our weight, is on the x-ray mistake, we have probability ft of making a mistake. And furthermore, we remove an epsilon times ft, fraction of weight, from the system, because all these guys, their weights got multiplied by 1 minus epsilon. So there was this portion, epsilon times ft, fraction of the weight, that got removed from the system, right? Because we multiplied them all by 1 minus epsilon. So we shrunk that. Good. So we remove epsilon times ft, fraction of weight, total weight from the system. So the final weight at the end, remember we were calculating W, which is the total weight in the system. Now we can really give a precise statement of what that looks like. It's exactly the initial weight times, which is m, times 1 minus epsilon f1. That's the fraction of weight we removed. This is the fraction of weight we removed at time 1. So 1 minus that's what we kept. So this is the total weight after the first step. This is the total weight in the system after this. Times that, you get the total weight in the system after the second step. Times 1 minus epsilon f3 is, we get the total weight in the system after the third step. That product is the total weight at the end. That's just exactly what our algorithm does. It's a product, so let's take a log to make it easier to look at, to convert the product into a sum. You take the log of this product, you get a log n plus, now this is a mess. For this product here, well, okay, the log of a product is the sum of the logs, so it's a sum over t of log 1 minus epsilon ft. That's a little bit of a mess, but let's just use the fact that log of 1 minus x is less than negative x, right? That's just a statement that, let's draw. Log of 1 minus x is this function here, minus x is that function there, and log of 1 minus x is less than negative x, less than or equal to. It's equal there. Okay? Right? So that's nice. Log of 1 minus x is less than or equal to minus x. So we can replace that with this here. Okay, so log of 1 minus epsilon ft is less than or equal to minus epsilon ft. Pull the epsilon out. And notice this here. What the heck is this? Sum over t of ft. That's sum over t. Ft is the probability we make a mistake at time t. Sum over ft is the sum over each time step of the probability we make a mistake. This is exactly our expected number of mistakes. Because ft is the probability we make a mistake at time t is equal to the expected number of mistakes at time t. This is the expected total number of mistakes. So what do we get? The log of the final weight is less than or equal to this log n minus epsilon times our expected number of mistakes. We again say if the best expert makes little m mistakes, well, its weight is exactly this, because every time it makes a mistake, we penalize with the hitting of the little hammer. We multiply it by 1 minus epsilon. So this is the weight of the best expert. The total weight in the system is bigger than the weight of any one guy. So the log of the final weight in the total weight in the system is bigger than the log of the weight of any one guy. And we just solve. So we get, this is log of W final is greater than or equal to this. And this is greater than that. We want to solve for capital M. So we move the capital M to the right, the little m thing to the left, and divide by the epsilon, and we get exactly that formula. This formula is just what you get from this by moving this to this side, and dividing. Right? And then you just do a little Taylor expansion of the log to get this quantity here. Okay, so that's it. That's it. Okay. So that shows that this algorithm does nearly as well as the best expert. Now it's really cute. Now what can we get from this? Let me connect this back to what we talked about earlier. So what we get is, okay, our expected number of mistakes is at most 1 plus epsilon times mistakes of the best expert plus 1 over epsilon log n. Here I had epsilon over 2. This little squiggle is not exactly a less than or equal to, because the second term in the Taylor expansion goes the wrong way. So to make it a strict thing, we don't need to divide by 2. Here, let's put that epsilon there. Okay, so our expected number of mistakes is at most 1 plus epsilon times mistakes of the best expert plus 1 over epsilon log n, so that's a true statement. If we set epsilon, so let's try to equalize the two lost terms here. So another way to write this is as follows. How well do we do compared to the best expert? We got an m here plus epsilon m plus this term that has no dependence on m. Just n, the number of experts. Right? We got an m plus epsilon m plus 1 over epsilon log. So we do best expert plus two things, an epsilon m and a 1 over epsilon log n. Let's equalize those two things. As we make epsilon small, epsilon m becomes smaller, but this 1 over epsilon log n becomes bigger. If we set epsilon to this quantity, that equalizes those two things. Okay, so if we knew in advance how many mistakes the best expert was going to make, we could have set our epsilon to this quantity. If we didn't know in advance, we could guess, run our algorithm. If we were wrong, we just cut it in half and run it again, and we'll lose an extra factor of 2. We'll just do a telescoping. You know, guess and double our guess of how many mistakes the best expert was going to make. Okay? If we do that, what we get is a bound of our expected number of mistakes is at most the number of mistakes of the best expert plus 2 times m root m log n, right? Because it's this thing, 1 over this thing times log n plus this thing times m. So we just get m plus this quantity here. Now, if we just make the following really stupid simple observation, which is that the best expert for sure makes at most t mistakes. If it makes t mistakes, the best expert is really bad. It means they all made a mistake, right? This is really, okay, so it's clearly the best expert is making a mistake at most t times. In fact, if just for every expert we just had another expert that says the opposite, then for sure it's at most t over 2. But okay. So anyway, the best expert for sure makes a mistake at most t times. So just plug that in. So this is less or equal to plugging in t, and you get exactly what kind of thing we said. The number we make our expected number of mistakes at most the best expert plus just replacing this with t, 2 root t log n. So what is our regret per day? So our per day regret, how many mistakes per trial are we making compared to the best one? Divide by t. Our regret is just this thing over t, and that's going to 0. Okay, so in other words, so our number of mistakes compared to the best expert, the difference is sublinear in t. It's like square root of t. So over t time steps per day, that over t is how many extra mistakes we're making per day is going to 0. And that's what we want. So that says that we're no regret.
Can you say again how it is that you deal with the fact you don't know m in advance
Oh,
when choosing epsilon?
yes, there's a couple of things you can do. The simplest thing to do theoretically is guess. I think little m will be 10. Do that. Run your algorithm, keeping track of what m was. When it reaches 11, say, oops, my guess was bad. Let me guess m will be 20. Restart from scratch and run again. And you just get a telescoping series. And you'll end up losing an extra factor of 2 in there. Restarting from scratch is kind of a funny thing to do. So you'd like to just actually keep the algorithm state and just slowly change the epsilon down. And you can do that also. It's just that requires doing an analysis directly on that. But the analysis we've already done says you can just guess and then double your guess if you exceed that. And you'll just, the total excess, how many mistakes will just be a telescope, will be a sum of these quantities up to m with an m over 2, m over 4, and so forth. So you'll lose an extra constant. I guess maybe you should multiply by 4 since it's going in the square root. Okay. But actually, you can have, so there's also been analysis of algorithms just over time, just basically over time you just want your epsilon to go to 0 as a function of what m has been so far. Okay, so what can we use this for? So we can use it to combine multiple algorithms, end up doing nearly as well as the best in hindsight for doing prediction. But let's go back, what about this thing about choosing paths? So what about choosing paths to work where our experts are different actions, not different predictions? So maybe our experts are, paths in a network or rows in a matrix game. They're not giving you advice. They're just different choices. So, we have a bunch of choices. Each one has a cost, say 0 or 1. So let's say every day each route is either congested or not congested, cost of 1 or 0. I claim we can still run the algorithm. And here's why. Rather than viewing the algorithm as pick a prediction with probability proportional to its weight, you can view the algorithm as just pick an expert with probability proportional to its weight. So instead of saying, you know, if 70% of the weight says up and 30% say down, then flip a coin with probably 0.7 say up, 0.3 say down. I could have instead said, look at the weights of the expert, normalize them to sum to 1, and then just pick an expert at random from that distribution and do whatever it did. Get its loss. If it got wrong, if it said the wrong thing, you get to say the wrong thing. If it said the right thing, you say the right thing. So for that, you don't need them to make, they could be just different routes. You have a bunch of routes, each has a weight, you normalize them to sum to 1, you pick a route at random from that distribution, you go with it, and if it was congested, then your route's congested. If it was not, then you're not. And everything works. So it's just because it's the same algorithm. So just the algorithm just choose expert I with probability pi proportional to its weight over the sum of the weights. Okay, and it's the exact same analysis because it's the same algorithm. In fact, we don't need to restrict the loss, the cost to be 0 or 1. You can have costs between 0 and 1. So now, how do you penalize an expert or a choice when its cost is between 0 and 1? Well, a very natural thing. So if an expert has a cost ci, just multiply its weight by 1 minus ci times epsilon. So if it has a cost of 0, its weight stays the same. If it has a cost of 1, its weight gets multiplied by 1 minus epsilon. If it has a cost of a half, its weight gets multiplied by 1 minus epsilon over 2. Okay, so just do that. And this actually, this also works with the same analysis. The reason is as follows. If you ask, what is our expected cost? Well, our algorithm is picking an expert with probability proportional to its weight. So our expected cost is exactly this quantity here. There's probability W1 over capital W that we picked expert 1. And if we did that, we would experience cost C1. There's probability W2 over W, we pick expert 2, and if we did that, we would experience cost C2. This sum is exactly our expected cost if we pick an expert with probability proportional to its weight. If you look at how we do our penalties, the amount of weight removed is exactly the sum of these epsilon CIWIs. That's how much weight is removed from the system. And notice that the amount of weight removed from the system is nicely connected to our expected cost. In particular, the fraction of weight removed from the system, namely this thing over capital W, that's the fraction of weight removed from the system, is exactly epsilon times our expected cost. So it exactly has this property we had before, that the fraction of weight removed from the system is epsilon times our cost. And so the whole analysis we had still applies. So the rest of the, once we have that, the rest of the proof is exactly from this route.
So let's say you pick the first route, and then so at the end of the day, you know the cost of all the routes, or just your route?
Yes. So I'm still assuming that we good. So I'm thinking of a model where at the end of each day we know what each expert's costs are, because we need to be able to do this penalty, this penalizing. So then we'll go to the bandit. Tomorrow we'll talk about bandit problem where you only get feedback of your own route. But it's right. This algorithm needs to know how well it would have done on each of the other because it needs to know how much to penalize them. Good. Okay. So just to recap, here's how the algorithm looks. And I claim it's a very simple algorithm. Right? You start with all the experts with weight 1. So you start with the uniform distribution. And you pick a random choice from the distribution. Say that one. World picks a column. You get this full feedback. So you find out the entries in that column. Imagine you're playing a matrix game. You don't even know. It's a huge matrix. You don't even know what it is. But when the world picks a column, you find out that column. We use that column to penalize. So we multiply every choice by 1 minus epsilon times its cost in there. Gives us a new distribution. Rescale to make it, to normalize it to sum to 1 and pick from that. So pick probably proportional to that. So we pick a new choice, day 2. World picks a new traffic pattern on day 2. We multiply by those and keep going. Okay? And our regret per time step is at most 2 root t log n, square root t log n over t goes to 0, just like we promised. And so we have this no regret learning. All right, so now we can drive to work. Okay, assuming full feedback, assuming we get the full feedback, right? So we'll later look at what if we don't get full feedback. Okay, so, yeah.
So you're making no assumptions about the costs of the experts, meaning that everything is adversarial. But what if the costs are distributed according to some, nice distribution? So all the costs are according to some Gaussian with different parameters, which you don't know. Can you do much better?
Okay, good. So the only assumption we're making right now is the costs are bounded between, say, 0 and 1. But like what if things were, say, a distribution? Right, so you can say better things if the world is nicer. And there are various sorts of results you can get as a function of, even adversarial, even without making assumptions in advance, you can say if I look back and find there was very low variance of some kinds, then you can actually get better bounds. You can get better bounds. So there's two things you can do. You can either make assumptions and get better bounds, or you can get a little more complicated bounds there as a function of how nice the world actually was at the end of the year. At the end of the year, you look back and say, you know, it was a pretty nice world. There were actually multiple good routes. You know, there wasn't a whole lot of variance in certain things, and you get a better bound as a function of how nice the world was. So absolutely. And there's lots of, so there's lots of things you can do. Yeah. Good. So now let me talk about some connection to this to games. I mean, you can sort of see it's an online repeated game, but I want to bring out a couple of connections today. So one connection is to two-player zero-sum games. So just to recap, right? So okay. So this is probably unnecessary, but so two-player zero-sum games, right? We have two players, you know, row player, column player. Games defined by this matrix, and I'm just going to write it where the payoffs are payoff to row, payoff to column. It's zero-sum, so the payoffs add up to 0. This is the matching pennies or the penalty shot game where we have a penalty shot with a shooter that can shoot left and right. This is the same as the world with the two, you know, up and down, but it's just different words, right? So it's a shooter who can shoot left and right, and the goalie who can who can dive left or right. And if the goalie, you know, gets it right, the ball doesn't go in. If it gets it wrong, it's a goal. Right. So this is Olympics. Yeah. So. Right, and so we know what a minimax optimal strategy is. So minimax optimal strategy, it's you know, randomized strategy with the best guarantee on expected gain over choices of the opponent. So it's you know, what to play if you think if your opponent is knowing you well, knows your distribution, and is going to do a best response to your distribution. Right, you know, and the minimax theorem says that every game has a well-defined value. Every zero-sum, two-player zero-sum game has a well-defined unique value. And in particular, this value v has a following property, that there's a strategy for the row player, the minimax optimal strategy for the row player, that guarantees expected gain at least v, no matter what the column player picks. And furthermore, there's a strategy for the column player that guarantees the row player gets at most v. So fixing the strategy the column player can publish in advance, so no matter what the row player does, the row player gets at most v. The column player loses at most v. Right? So that's a minimax theorem. And it's kind of counterintuitive because it means that against an optimal opponent, it doesn't hurt to publish your strategy in advance. And actually, historically, it had been proven for small games, but people thought it was false in general, and so they you know, so it wasn't expected. So we can actually get a proof of the minimax theorem directly from our regret bound. Okay. And I just want to show you that, and it's because this kind of gives a little bit of a feel of this. So here's a proof of the minimax theorem using what we just proved about randomized weighted majority. And the proof goes as follows. Suppose for contradiction the minimax theorem were false. What would that mean? That would mean that there would exist some game with two values, one bigger than the other, VC bigger than VR, with the property if the column player had to commit, so you're the row player, if the column player had to commit first, then, and you got to C, you could always do a row that got you an expectation at least VC. But if you had to commit first, if you had to pick your distribution first, and then the column player got to pick the best column against it, it could ensure that an expectation you make at most VR. And there would be a gap between these two if the minimax theorem were false. So suppose there were such a game and there was such a gap. Okay, let's take that game and normalize the entries so they're all between -1 and 0. So they're all costs between 0 and 1, just like we were talking about. And let's say this gap is delta. Okay, why couldn't this happen? Okay, so now consider playing the randomized weighted majority algorithm as a row player against a column player who plays optimally against your current distribution. Okay, so you're playing the randomized weighted majority algorithm, and what's the guarantee we showed? We showed that in t steps, our algorithm is going to do nearly as well as the best row in hindsight, minus at most this much. That's what we proved. Now, what do we mean by best row in hindsight? We played this game for over the course of a year. You know, What's it mean, the best row in hindsight? Best row in hindsight means look at the empirical distribution of the column player. The column player out of those 365 times, 52 times played column 1, 67 times played column 2, and so forth. Look at that empirical distribution and pick the best row against that. So we've fixed the column player's empirical distribution, and now we're doing the best row against it. So we should be able to get the top value. We should be able to get the VC, because we fixed the column player, and now we get to pick the best row. So we should be able to get an expectation VC for each time step, or T times VC total. On the other hand, our algorithm should make at most T times VR, because every time we play, the opponent knows what distribution we're going to play from. We committed to playing randomized weighted majority. It's a different distribution each time step, but that's fine. Every time step our opponent knows it, because our opponent was also sitting in class. Our opponent knows the algorithm. Our opponent knows at time 17 exactly what distribution we're going to be playing, and it should be able to, so it knows it, so it should be able to force us to get at most this much. Okay, and there we get our contradiction, because we should make it most this much, but we're getting nearly as good as best row in hindsight. Best row in hindsight's at least this, and this is bigger than that. Okay, in particular, the gap between these two is delta times t, and that contradicts this gap once delta times t is bigger than this quantity here, or solving for t once t is bigger than this much. Okay, so that was this, so after this many steps, our per day regret is smaller than delta. And that shouldn't be possible if the minimax theorem were false. Right? So in some sense, it's a very constructive sort of, we are doing nearly as well as the best we could have done in hindsight. I mean, it means there's got to exist something that form. Okay. So I think it's kind of a cute proof. So, okay. So, right. So another thing I just want to mention is, so randomized weighted majority, actually you can think of this as giving you a fast way to compute approximate minimax optimal strategies if you can simulate a best response oracle quickly. So in fact, many of the current fast algorithms for things like finding approximate maximum flows in networks work by running a multiplicative weight algorithm against an oracle that uses a fast linear system solver in an appropriately defined game to get approximate max flows, and so they kind of work this way. Okay, we're done. Yeah. So I'm trying to figure out. Okay, so good. Okay, so that's from I was thinking about whether to talk about coarse correlate equilibrium, but I'm going to do that. What I'm going to do is talk about correlate equilibrium and coarse correlate equilibrium and that sort of thing. So I haven't yet talked about what happens if you have many players and they're all minimizing regret. This was just two players this is one player against an kind of an adversarial or unknown world. We're just kind of thinking of us against the world. We're not thinking of the world as a bunch of players. We're just thinking of the world as something. And maybe out to get us, maybe not. Tomorrow I'll talk about, so what if we have many players and they're all minimizing regret. What I want to do for the rest of today, for the next 25 minutes, is talk about this problem of what if you only get your own choice as feedback? What if you don't find out how well you would have done had you done something else? Okay, so let's because that's just a really nice algorithms for that. We're going to, okay, so one thing is, notice that our regret bound had a log number of choices, which is really great. Log n is like how many bits it takes to just write down the best choice. So it's a nice sort of information thing there. If you only get feedback for your choice, there's no way to have the log n. If there's n choices, you got to at least try each one. Like what if they're all bad except for one? It's just really simple world. Every route is bad except for one. And you only find out the feedback of your own route. It's going to take you, at least n over 2 steps on average until you find that one good one, right? Whereas in hindsight, you should have been using that one good one all the time. Okay, so everyone see that even the very simple case, the one perfect route, all the rest are bad, always. If you only get feedback for your own choice, you try this, not good. Try this, not good. Try that, not good. Try that, not good. Try that, not good. Is there anything good? You got to try until finally you find the good one. You're going to have to lose that n over 2. Okay, so excuse me. All right. So we're going to have to lose an n, not a log n. Okay. So just for fun, I want to use a different motivating example to talk about this. So, okay, so I want to talk about this work of Auer, Cesabianchi, Freund, and Shapiri, where what we're going to do is take the algorithm we've already looked at, this randomized weighted majority, and apply it to the setting where we don't get full feedback. So we're going to use it as a subroutine to solve this problem where we only have very limited feedback. Okay. And then the regret band will have this extra n in there. This cumulative regret. Before we didn't have this capital, this n there. So the average regret has an extra n there. I'm going to do a little weaker version of their analysis where rather than this power 1/2, it's a power 2/3. It turns out the same algorithm, but just to get this 1/2, the analysis is more grungy, and I want to do a simpler analysis, so it's just not going to get as good of a bound, but you can look at their paper. And just for fun, I want to talk about in the context of selling stuff, because we're talking economics, so let me talk about in the context of selling stuff. Okay? So just consider the following setting. Imagine that, say, rather than thinking of yourself as driving in the graph, think of yourself as you're selling lemonade or bottles of water. Okay, so I gave this at something in China, in Shanghai. There was a World Expo there, and if you go there, you'd see that bottles of water were actually quite expensive. It was a hot day. Okay, so imagine here you are, you're selling lemonade, and you're not sure what price you should sell it for. And imagine we have the following setting that for t equals 1, 2 up to capital T, a person comes by, and we get to post a price that how much we're going to sell lemonade for. They come by, and they buy or they don't. So we set a price for our lemonade. The buyer arrives. They have some amount that they think lemonade is worth. If their value is bigger than the price, they buy it. Otherwise, they don't. And then we repeat. So we change a different price and go on. Oh, yeah. This comes from, there's a cartoon where there's a kid with a stand, and he has lemonade, $500 a glass, and someone comes like, what the heck are you doing? He says, I only have to sell one, and I'm done for the summer. Okay. So, right. So okay, now suppose that the values were revealed to our algorithm as the people leave. So they come by, they buy our lemonade or not, and as they go, they say, you know what, I would have bought had you priced at $2 or less. Suppose we get that feedback. Then we could imagine competing with the best fixed price in hindsight by just setting up a separate expert for every price level. You know, 0, say our price levels are in increments of, I don't know, dollars or pennies or whatever, say in quarters. So could sell for a quarter, 50 cents, 75 cents, $1, $1.25, $1.50. Let's say those are our price levels. And we just set one expert for every price level, and we could just run the algorithm we had. The person told us they would have bought at $2, so that means we would have made $2 had we sold at $2. We would have made $1.75 had we sold $1.75. We would have made $1.50 had we sold $1.50. We would have made 0 had we sold anything at any price bigger than $2. Okay, so I'm modeling people as having a valuation. If the price is too high, they don't buy, and if it's lower, they do buy. Is that everything okay there? Yeah.
Do they tell us our valuation if they do buy?
Yeah, let's say no matter what, let's suppose, just for the second, I'm going to get rid of this in like 10 seconds, but suppose as they leave, they tell us what their valuation was either way. Then we could penalize our experts appropriately, because we would know how much we would have made had we, used that price. Okay. But now what I'm interested in is what if we don't get that information? We just find out they bought or didn't buy. So we know that if, say, they didn't buy it at $3, so we know that we made 0. But we don't know whether they would have bought at $2.50. We actually, in this scenario, get a little bit more information, because if they didn't buy at 3, they wouldn't have bought at 4, 5, 6, or 7 either. But actually, I'm not going to use that information. I'm just using it as a motivating example, and just imagining that the only thing we get back is we chose 3, they didn't buy, we got 0. Or they did buy, we got 3. Great. If they bought at 3, we know they would have bought 2.5 also. So there's actually more information here than we're going to use. Our algorithm is only going to use the feedback on its particular choice. Okay. So what can we do now? Just like before we had to assume, all the costs, you didn't fall off a cliff. Here I'm going to assume that, Bill Gates is not really thirsty and in the audience, so that there's some upper bound on how much money we could possibly make on a single glass of lemonade, and then we know that in advance. Okay? So assume all the valuations are upper bound by some high value h. Okay, and so our goal is revenue nearly as good as the best fixed price in hindsight. Okay, so does that make sense? So maybe just one thing I just want to just really briefly mention is if people were coming from a distribution that we knew, so if in fact there was a distribution on buyers' valuations, I mean, in the end there will be empirically some distribution. Notice that actually here we don't even know. At the end of the year or the end of the day or whatever, we don't actually know how many people are willing to pay different amounts because we don't get that feedback. We just know if we sold or not. But suppose we knew how many people were willing to pay different amounts. So this is a number of people willing to pay P. Okay? So what I mean by that is, right? So this will be some decreasing curve, right? How many people are willing to pay 0? Well, how many people are willing to pay 1, last 2, last 3, last, right? How many? Suppose we knew that distribution. Then what price should we set? Well, we should just set the price that maximizes the area under this curve, how much money we make per lemonade times number of lemonades we sell. Oh, I guess I should mention, I'm assuming our marginal cost for lemonade is 0. Suppose it costs us, 27 cents to make lemonade. Just call that 0. Just subtract that from everything, okay? That's when I call it 0. so let's just, so I want to equate revenue and profit. Okay. So then we could just pick the P that maximizes the area under this curve. But the point is we don't know this. And we're trying to compete with that. So we're going to try to compete with the best fixed price in hindsight. Okay? All right, so ready to sell lemonade? Actually, I had a student in my class use this for, okay, I don't really know these things, but I guess on World of Warcraft you can sell stuff and make money, right? So anyway, okay. Right. Okay, so here's the algorithm. What we're going to do is our algorithm is going to sit in between this randomized weighted majority algorithm and the real world. Remember, the randomized weighted majority algorithm is expecting full feedback. So we're going to have to interface with it and give it a pretend world in which there's full feedback. So here's how it's going to work. The randomized weighted majority algorithm is going to give us a distribution over X. It's going to start with the uniform distribution, everybody with the same weight. We are going to modify that distribution P to a different distribution Q. We're going to pick an expert, pick a price from a distribution Q, and use that price. The buyer is going to maybe buy or not buy. We're going to end up with some gain, some quantity. It might be 0, it might be non-zero, it's going to be some number. It's just a feedback for what we actually did. We're going to somehow have to convert that into a vector, a gain vector, because randomized weighted majority is expecting this vector over all the choices. We talked about in terms of cost, but you can also do randomized weighted majority in terms of gains. Like what if you have gains of cost? Everyone okay with that? I claim, just believe me, that you can do it with gains instead of costs. It's all just you shift everything. So we're going to give it a gain vector. So this is living in a fake world. It thinks it played P, and it thinks there's this gain vector G hat. And now, okay, so how are we going to do these things? Let me just tell you what we're going to do, and then we'll talk about why we're going to do it. Okay, so what are we going to do? First step. How do we convert the distribution P that the algorithm gives us into the distribution Q that we use? All we're going to do is mix it with the uniform distribution. Think gamma is some small number. We'll figure it out later. Think it was 0.1. What we're going to do is probably 0.9, pick from P, probably 0.1, just pick a uniform random expert. Okay? That's how we get Q. We're just going to take 1.9 times P plus 0.1 times uniform distribution, add them up. That's going to be our distribution Q. That's how we're going to select the expert, or let's select the price. How are we going to give a gain vector back? Here's what we're going to do. We chose expert I, we got gain GI. We're going to fill out a vector by giving zeros for all the choices we didn't make, And the one we actually did, we're going to take the gain we actually got and divide it by qi. That seems like a weird thing to do, perhaps. But let me tell you why this is somewhat natural. This gain vector that we give back, that's actually a random variable, because the vector we give back depends on our choice fixing the buyer. The gain vector we send back to the algorithm depends on the expert that we chose from Q. So this is a random variable, this vector. What is the expected value of the first coordinate of this vector? Well, there is a Q1 probability that we chose expert 1. If we did that, if we had chosen expert 1, we would have gotten gain G1. That's the gain of expert 1. And then we would divide that by Q1 and stick it there. So with a Q1 probability, we would have stuck G1 over Q1 here. And with a 1 minus Q1 probability, we would put a 0 here. So the expected value of the first coordinate is Q1 times G1 over Q1 plus 1 minus Q1 times 0. So its expected value is G1. The expected value of the ith coordinate is exactly Gi. Because there's a Qi chance that we actually did it, and then we put this number in there, and a 1 minus Qi chance we didn't do it and put in the 0. So this vector has the property that for any given entry, I, the expected value of that entry over our random choice of expert is exactly the actual gain for doing that. Okay. The other thing is these numbers could get, most of them are zeros. This one could be big. Why could it be big? Because Q1 could be small. Qi could be small. We promised that all the actual gains were between 0 and capital H. This Q could be kind of small. How small could it be? Well, we have gamma times uniform distribution. Uniform distribution has 1 over n probability on every choice. So Qi is at least gamma over n. So the smallest this could possibly be here is gamma over n. So dividing by that, the biggest this whole thing could possibly be is h times n over gamma. That's actually formally the reason why we add this uniform distribution in. If we didn't do that, the p's could get very close to 0, and these quantities get very high and go to infinity. Okay, and we don't want that. We need a bound on how big these can be. All right, I'm now going to give you the analysis of this algorithm in this part of the slide. The font will be a little small. Okay, so how are we going to analyze this thing? So there's some actual optimal choice in hindsight in the real world. The randomized weighted majority is living in a fake world. It calculates its own opt-hat. Opt-hat is defined with respect to these gain vectors g-hat. It thinks it played p. It thinks it got gain vector g-hat. It thinks it got reward p dot g-hat. That's what it thinks its expected gain is, p dot g-hat. It thinks that there's an opt-hat, which is the best coordinate of the g-hats. We need to relate our gain to this guy's gain. We need to relate opt and opt-hat. The way we're going to prove we do nearly as well as this guy we've proved does nearly as well as opt-hat, and opt-hat is nearly as good as opt. Therefore, we do nearly as well as opt. Okay? Good. Let's look at this algorithm here. It believes it got gain p dot g-hat. It got gain vector g-hat. It thinks it played p vector, thinks it got g-hat, thinks its gain is that. Let's just plug what that is. These are mostly zeros, except for this entry here. So it thinks it got a gain of pi times this quantity here. Let me just call that the gain that randomized weighted majority thinks it had. We proved that the randomized weighted majority algorithm does nearly as good as opt, or its opt. We did in terms of losses, where it was, cost less than or equal to opt times 1 plus epsilon plus 1 over epsilon log n. These are gains. We get gain at least opt divided by 1 plus epsilon minus 1 over epsilon log n. Now that 1 over epsilon log n was assuming everything was scaled to 0, 1. Things are not scaled to 0, 1 anymore. They're scaled to 0 up to nh over gamma. So there's an extra nh over gamma sitting in there because the things aren't scaled to 0, 1. They're going in the range 0 up to nh over gamma. So that's what that's.
Sorry, I don't understand how the randomized weighted majority algorithm knows what Q is, because the Q's are not something that is easy.
Oh, yeah, it does. It does. I'm just calculating what, this is just, it sees g-hat though. So it can compute this dot product. So it sees this, it thinks it did this, it sees this, so it can compute this dot product. It just happens to equal this. It doesn't know what that is. That's right. You're absolutely right. It doesn't know what those are. So it thinks this is its gain, and the proof we gave shows that's nearly as good as opt-hat, where opt-hat is the best, fixed choice under all the g-hats. Our actual gain was GI. Now GI is close to GRWM because, well, GRWM is defined this way, so we can just, so GI is this thing times QI divided by PI. Right, so GI is just this guy here times QI divided by PI. And QI is never much lower than PI, because remember, Q is 1 minus gamma times P plus something else. So QI is at least 1 minus gamma times PI. So this quantity is at least 1 minus gamma. So our gain is at least 1 minus gamma times RWM, whatever RWM thinks it got. Good. So our gain is nearly as much as RWM's gain. RWM's gain is nearly as much as opt-hat. Opt-hat is a random variable. It's a random variable because it kind of depends on our choices. But the expected value of opt-hat is actually at least as good as opt. Why is that? What the heck is the expected value of opt-hat? Well, for any given coordinate j, the expected, I'd mentioned before, if you think about any given coordinate j, the expected value of gj hat is exactly gj. There's 1 minus qj probability we didn't do it and put a 0 there, qj chance we did do it and put in gj over qj. Any given day, the expected value of the jth coordinate is the actual value of gj. So what the heck is the expected value of op-hat? Op-hat on any given run is just the maximum over experts of how well that expert did over all time. It's the maximum over experts of how well that expert J did in its fake world over all time. The expected value of opt-hat is, imagine we replayed the algorithm, we replayed the movie with different choices, different randomized choices. We did time 1, times 2. On time 1 we did it, and we got certain, okay. Let me say it again. Right. This is a random variable. The expected value of that random variable, the expected value of the max is greater than or equal to the max of the expectation. Okay, why is that? Right, so this says, these two quantities. Imagine we replay this movie, we try it again, but with different random choices, the same world, same sequence of buyers, but with just different random choices. Each time, we'll get maybe different GJ hats. This quantity here says in each of those worlds, we get to pick the best J for that world. This says you have to pick the same J every single world. It's the max over the expectation. What J does best on average over all those worlds. This says, on average over all those worlds, take the best J for that world. So this is better. This gives more flexibility than that one. Expected max is greater than or equal to max expectation. And max expectation equals opt, because the expected value of the sum is the sum of the expectations, and the expectation is gj. So this is exactly, this expected sum of gj hats is exactly just the sum of the gj's. This is just how well expert j did. This is exactly how well expert j did, because expected value of gj hat is how well expert j did. So this is just how well, this is just max over experts, how well expert j did. That's exactly opt. Expected value of opt hat is at least as good as opt. So what do we have? We do nearly as well as randomized weighted majority. Randomized weighted majority nearly as good as opt-hat. Expected opt-hat at least as good as opt. So our expected total gain is nearly as good as the opt. So we just combine all these together, plug in gamma equals epsilon. Our expected gain is at least opt times opt over 1 plus epsilon squared minus 1 over epsilon squared times this quantity here. We're worse. Okay, let's see, two things. This is n here. There's epsilon squared there. The epsilon squared, before we had 1 over epsilon, now we have 1 over epsilon squared. Why do we have a 1 over epsilon squared? It's because we lose a 1 over epsilon here, and we lose a gamma here. If we set gamma to epsilon, there's a 1 over epsilon here and another 1 over epsilon there. We can't make gamma too big because we're losing here. So we need our gamma to be something like epsilon. So we lose 1 there and 1 there. So we lose 2 of them. Okay, and so when you equalize the two quantities, you end up with an op to the 2/3. So you end up, this is the t to the 2/3 thing. If you do a better analysis, you don't analyze in terms of just the maximum, but you look at variances, then you can reduce that to square root. And so you get this thing that I promised. So that's how we can handle this bandit. Okay, so good. So maybe so this tells us, so we can use this now. We can so now we can do things like, selling our stuff or driving to work, where we only get feedback from the action that we chose. All we have to do is run weighted majority, where we mix that with a little bit of uniform distribution, and then we take our actual cost or our actual benefit, and then we scale that by the probability we chose, we used for choosing that in order to get the expectations right. That makes the numbers get larger because we're taking some quantity and dividing by a probability, which could be somewhat small, but then allows us to run the algorithm, and we get nearly as good as the best in hindsight, but now we've got this extra n sticking there. Okay, so let me end here.
Questions for Avrim?
Am I right to think that by adjusting gamma over time, you can do this so that with a single infinitely long run of the algorithm, you'll satisfy this this error bound for all t simultaneously?
Yeah, I'm pretty sure. So I know that's true in the non-bandit case, and I'm almost positive it's true in this case too. You can also do a guess and double. You can also pick some value when, actually, okay, it's a little bit trickier actually to do a guess and double since you never actually know here how well the best one's doing. But you do know t, so you know how many times you've played so far. So yes, the answer is yes. I don't know the right reference, but the answer is yes. In fact, probably in their paper, I'm pretty sure actually. That's a very nice paper, the X3 paper. And so I'm pretty sure.
Is there research into strategies for the experts or perhaps teams of experts to steer the person doing the RWM to the worst case performance? If there was an antagonistic expert.
I mean, let's see. So, not that I know. I mean, there's okay, so I don't know of any like that. I mean, the closest I can think of related to that might actually be something like some work of Ariel's actually on what if you have a learning algorithm where various entities have their own interests in mind, and it's more where they want you to predict well on their data kind of problems. Yeah, so usually here we're just thinking of this as a kind of a generic way of combining different choices. You give me some choices, and kind of the bottom line here is that if I have a bunch of choices, how much is it worth to know in advance which choice is right? If I can play many times, I can actually have a regret that goes to 0, and so without knowing in advance which one is best, I can lose. So if I'm playing with many time steps, I can act as if I knew in advance. If I'm playing a small number of time steps, then these bounds, if this is big compared to opt, so the amount you're losing is more than the amount you're making, this could be a vacuous statement. This is only an interesting statement when this quantity here is a lot bigger than that quantity there. So,
just going back to the full feedback case for a moment. So you said that once you pick your option at the end of the day, the world cannot look at what you did and then based on that reveal what the cost was, right? But I don't actually see why that matters.
Oh, yeah. So actually, these analysis you can do in settings where, say, the next day's traffic, the next person depends on what you did before. Now, today's, it can't be that you make your choice and then the world sees that you chose $3, so it's going to give you someone who wants to buy it at 500, and when you sell for 500, they give you, so they can't, or give you 299. They can't like see what you're doing today and then give you somebody today that's, you know, based on your choice. So it's not like okay, if you're playing rock, paper, scissors, right? So I can't, okay, you go first. You know, you play rock, okay, now I'll play paper. Okay, but I can look at your performance in the past and what you did in the past and decide what to do the next day. There's, things get a little trickier in the bandit case because if they know, in the bandit case, they know what information you have. And so this information aspect gets a little bit more complicated. But you can handle all those things as well. Yeah. I guess the issue I didn't want to get into is the regret measure, doing nearly as well as the best performance in hindsight, is a little slipperier if the way the other person is playing depends on what you did. Imagine you're doing repeated prisoner's dilemma, okay? And because of your behavior, the other person ends up defecting all the time. And the best you could have done is defected all the time also. But had you been nice, they would have been nice. This does not get at that issue at all. It doesn't say, had I played differently, the world would have been nicer to me. This does not handle that aspect.
But, so I get what you're saying, but I don't see how that's captured in the way you presented it, because like, the world doesn't have to commit to the cost of all possible choices that I made before I made the choice, because those numbers are only going to be revealed to me after I make the choice, and I'm not going to use those numbers, whatever the world committed, right?
Yeah, so we're really only using that each day the world picks a cost factor, we pick something, and we pay the dot product, and we want to compare it to the expected value. So we had to compare, you know, our probability of making a mistake to the amount of weight removed in the system when we looked at the right.
Only use that cost factor at the end of the day, right?
That's right. So that's absolutely right. That's right. That's right. So we just need that each day the vector is picked first, and then we pick our choice.
Yeah. So that's still where
Maybe we should take this one offline, see if there's more
sure.
questions. Yeah.
So that was something, if I was selling something really expensive like a car, I could imagine maybe I'd want to first figure out, I mean, kind of said, right? You first figure out maybe for the 100 before you figure out for the $10 what you would want to do, right? Like if you're in a setting, is there a natural way to increase in as you kind of zoom in on what the price will be?
Yeah. So they're right. So for example, even in the full information case, you can, rather than start with the uniform distribution initially, you could start with non-uniform. So imagine that, you know, you could even imagine a case with an infinite number of experts, kind of more precision. You could start with some distribution that's non-uniform, and then what the log n gets replaced by is log of 1 over the initial probability that you put on that choice. So in other words, imagine that I have some belief about the world. Say I have some belief about the world. I think this one is likely to be good. I think that one is less likely. In the end, how well am I going to do compared to expert I? Nearly as good as him minus something. It depends log 1 over pi, how much probability I had on him. So if I had a good sense of things, so that's one way to handle that. And absolutely.
So you can think of a couple, so the lemonade situation is obviously a situation where you have a little bit more than just a bandit problem, but not quite full information. Intuitively, it seems like there might be a way to encode some of that information in the gain vector. Would that be possible,
Yeah.
and how would that affect the analysis?
Yeah, so you could do that. It ends up not helping a whole lot. So for instance, one thing you can do is, well, rather than saying your experts to be like $1, $2, you should maybe do them multiplicatively, because like powers of something. Say you do them as powers, like powers of 1.1. So now the problem is that it gives you local information, but doesn't give you, right? So you can do it, but I think it doesn't help sort of too much. But you absolutely, you can do it. If the range was small, maybe it would help more. It's certainly right. There's certainly cases where you do get in-between kind, and you could potentially, right, modify the algorithm and try to take advantage of it. I mean, absolutely makes sense.
And let's thank Avrim for the discussion.